it's a time for us to go for the next lecture, and it's honor to me to introduce the Gregor Schoner, who is the head of Institute of Neuroinformatics at Ruhr University of Bochum. It was a pleasure for us to organize together a summer school last summer, and I hope it's not the first, but it was first, but not the last project we did together. And today we have an opportunity to hear from him a new lecture on how cognitive emerges from sensor motor pressures and neural dynamics perspectives. So please welcome Gregor Schoner. So you have 40 minutes for your presentation.
Thank you, Alexander. I hope I'm heard. Yeah,
yes,
sounds
yes.
Okay, good. And I think I probably can share my screen. I hope you see now my slides. I'm going to put them here. Let me just make a little rearrangement here, like this. And go to, also, I hope you see my slides now, right? Okay.
Yeah, sure.
So a pleasure to participate in this meeting. It's a radical change of topic. I'm at the other end in the sense of the spectrum that you have in this talk, maybe closest to Stefano Nolfi, who will be talking a little later. So I'm someone who thinks about essentially, you could say, artificial intelligence in the action domain, in what we call embodied in the sensor motor domain, and thinking about that with neural methods, the neural inspiration. So if you, many of you are interested in autonomous robotics, so robots that act based on their own sensory information about the world. And by that, you typically mean going beyond just autonomous control, really doing things like decision making, generate sequences of action to solve problems, right? And the classical notion of that was, of course, that you would have some information about the world that you model, extracting elements of that model from some sensory processes. And on the basis of that model, you would use the planning techniques that essentially classical artificial intelligence was about, and then act that out. And that matched, when that approach was developed, was actually the same time as artificial intelligence was developed. And it matched the view of cognition, including of human cognition, as essentially computation, abstract invariant representation symbols and their manipulation based on rules, the computer metaphor, the computational metaphor, that amounts to function evaluation theoretically, that functions can call each other and pass information on and so on. And that was a very developed part of artificial intelligence. And robotics sort of moved along with that. In fact, some of you may know from textbook history that one of the first autonomous robots, Shaky, was very much in that paradigm. And Shaky very famously had a hard time perceiving the environment. That was the costly part. It's sometimes called the symbol grounding problem. So how do you link these symbols to sensory and ultimately also motor experience? That has turned out harder than expected. And for a very long time, it was a strong limitation on autonomous robotics. And I'll point later to new optimism that comes from probabilistic methods and from deep learning approaches. But this difficulty led to criticism of that classic approach. It was maybe most articulated in the wave that was called behavioral-based robotics, late 80s, in the 90s. Rodney Brooks was perhaps the most vocal critic. And the idea was to renounce to these general world models and use perception only as specific sensory inputs to individual behaviors that were often very elementary kinds of behaviors, like just obstacle avoidance or roaming behaviors. And then to chain up these behaviors, organize them in some simple form, for instance, that they could compete with each other. Maybe they could sometimes provide input to each other, chaining them up. In terms of the analogy to organisms, this was more going to the levels of almost reflexes, chaining up reflexes, like Sharrington's old idea that behavior is a chain of reflexes. Not rigorously, it was sort of inspired roughly by these lower levels. And it was very successful in the sense it did get robots acting and moving and going. And in fact, the most popular commercial autonomous robots today are vacuum cleaners, right? And they are sort of in that fold. They are organized around this kind of idea. I just want to point out that some of the ideas I'll be talking about have their origin in that metaphor. So we developed methods that use nonlinear attractor dynamics with instability, somewhat like I will be talking about later. In fact, we already used neural fields or peaks of activation in neural fields in that spirit, where we had different behavioral levels, and we were doing vehicle obstacle avoidance and things like that in that spirit. Now, the difficulty of that approach was it didn't turn out to be hard to scale up, and not surprisingly, perhaps it was difficult to make these do the more complex behaviors, the sequences that lead to goals. They were essentially good for these low-level things, especially where cognition enters, where you act on sensory information that is no longer immediately available. That's what we call memory and knowledge about the world. That was particularly hard to integrate. And just say that the standard solution right now is to combine these approaches to have a reactive layer that's behavior-based and to have a classical planner higher up, which means that problems in both domains actually have to be solved. So it's not really a fundamental solution. Now, interestingly, in human cognition and neuroscience, a parallel revolution occurred, or a reaction against the classical view that runs under the label of embodiment. And it's based on the insight that cognition emerges in evolution and in development when the children acquire cognitive skills, really emerges from sensory motor processes. So for instance, memory in biology, memory really emerges from spatial navigation. All kinds of animals know where their nest is, where food is, where danger is, and they build maps like that. And so that's memory in the sense that they need to know that without immediate sensory information about it, because it might be out of reach. So they have to navigate there, right? And that's where you need the capacity to use past sensory information to structure behavior, and that's what we call memory. And similar decision making really emerges from action selection. Now, a lot of animals have some discrete categories of behaviors they can activate at any moment in time, and they have mechanisms of how to prioritize that and how to sequence that. And that's the foundation for a lot of things that we call cognitive decision making. And take here an example of my kids playing soccer to make it plausible to you that a lot of embodied cognition is grounded in activities like that. And if you think about this activity, you can see it's actually very cognitive. It's as cognitive as chess playing. You have attention. You control gaze. You're selecting the environment objects to attend to. Perception is active for a purpose. You're not just taking inputs. It's all based on working memory, because you can't do a complete visual search of the scene every time you want to look at something. So you use working memory to make this much more efficient, to already narrow down the region that you have to monitor. And then of course, you have action plans, sequences, you make decisions. The whole thing is actually goal-oriented, even quite literally. And there's a lot of knowledge in this activity. For instance, a lot of knowledge that we might know to understand the rules of the game, which is maybe the most elementary form of knowledge, but subtle knowledge like how slippery the ground is, how hard can you tackle your sister, and you learn from experience, you learn autonomously. You can't prevent yourself from learning actually as a human being, which is the form of learning that we have actually not yet achieved in artificial intelligence. It's not supervised, it's also not preparing stimulus material, it's really just from experience that you learn. So a lot of cognition in this very simple activity. And because it's sensory motor, it has the properties of sensory motor processes. So for instance, all of these behaviors have to have some form of graded state inside, because and evolve in continuous time, because they can link to sensory and motor processes in continuous time, or they do that intermittently, at least. And they also take place in closed loop, which all of you know requires stability, requires dynamics. And in this field of cognitive science, people have started to speculate that perhaps all cognition is sort of like that even chess playing ultimately is sort of like that. And some of you might know that in chess playing, it does matter how the spatial arrangement is communicated to you. It's different if you play in the park in a major setting versus on a chessboard, for instance. So the notion is that the processes that support cognition have these same kinds of properties, so are ultimately dynamic rather than function evaluators. And that would actually eliminate the symbol grounding problem, because it would mean that all representations are grounded all the time. And it sort of inverts the question. Rather than say, I have symbols, manipulate them, how can I ground them? You say, well, how do seemingly abstract, discrete things like events and categories emerge from grounded, neural dynamic processes? So that's the vision we embrace, and there are a couple of people do that from different perspectives. And a major approach, that maybe the most elaborate approach, is really to approach cognition and artificial action based on analogies with the nervous system, to use neurally inspired approaches. You're all familiar with, I assume at least somewhat familiar with deep learning. Connectionist thinking. And I want to first base my tutorial on that. So in connections thinking, you think of artificial neurons, abstract neurons, as input-output elements. They're essentially just some inputs, weighted inputs perhaps, and threshold them and pass them on. So only the thresholded activity going through a sigmoid is passed on. And so you can chain up units like that into forward networks that then generate outputs that are complex functions of input. Some of these networks are universal approximators that can represent just any function. So as such, these networks are still very much function-oriented. I'll refer to a particular way of using that kind of notion that we use. For instance, if you have a sensory surface, let's say this would be your retina, your cochlea, you could have a regular pattern of connectivity that makes that certain features on that surface, here's just the location on the surface, are represented by a group of neurons. They would have certain tuning curves, and for instance would come to represent a stimulus located around here as a localized piece of activation. Somewhere else, the peak would be somewhere else. That would be called a space code, because different patterns of activation here at this level stand for different situations on the stimulus surface. And the population of neurons here could be considered a neural map. It's often called a feature map, or we call this a neural field, because we neglect the discrete sampling of these spaces by neurons. We smear them out into a continuum. So that's the notion of neural fields. It's a low-dimensional neural network in the sense it represents only some simple dimensions like sensory features and so on. You can have the same thing the motor end. You have, in the motor case, motor parameters would be represented by projecting onto the motor system. If you look in more detail, the motor system is actually always a little bit different. It's always the dynamical system. So it always has an attractor, stable state that somehow specifies the state of the motor control. You all know that you need control to get any motor action going. And in the nervous system, it's actually the peripheral reflex loops that provide sort of the minimal stabilization mechanism for any motor action. So you can have motor fields and you can have perceptual fields and kind of stuff in between. And that's what we will be using as our language. But this aspect is still the feed-forward aspect, the mapping aspect. On the other hand, if you really want to get a neural network to do something autonomously, to generate activation patterns, ultimate behavior that's not just dictated by some external input, you need to get activation generated endogenously, that is within the network, without a need for external input. So for instance, to generate movement. It's not just reflex-like, or to create working memory, that will be activation that persists in the absence of input, or to generate decisions in sequences. And so the notion is that that is possible in recurrent networks. And I'm talking about strong recurrence in the sense there can be more activity created by loops of neural connectivity than by the input. So you can imagine if you have some architecture like that, then the output driving the system can lead to some kind of reverberation and ultimately keep activation going or get it going. And the important thing about that is that that steps away from the input-output mapping idea, because you need some notion of time to make this feasible, right? The output needs to be present before you can actually say what the output is, and the only solution to that is that it's the output at some earlier time that serves as input when you compute in your output. In the nervous system, of course, this is not discrete iteration like that. Time isn't iterated. Actually, spiking isn't iteration. Spiking is asynchronous. So it's really what we would. It's really continuous time, and that's what we call neurodynamics. And biophysically, this comes ultimately from the membrane potentials, or you can also use the spiking rate to represent that, and has some form like this here, where the rate of change of activation is a negative function of activation, which really gives the system stability. So inverse proportional control, if you wish. That's really biophysics. Neurons are like that, and that is inherited by populations. And all the connectivity that you usually think of as providing the output are contributions to the rate of change. So input is here a forcing function on the right-hand side of the equation. Here, this self-excitation, for instance, would be a coupling where the activation itself passed through a sigmoid would be an input, a driving force. So that's the notion of neurodynamics. And we'll use this notion in our attempt to create cognition out of these networks in the form of dynamic neural fields. They have interaction. So you see the equation is very, this is one sort of standard equation we use as this generic form where, again, the minus u term, you have some external inputs. H is usually the resting level, some constant. And here are couplings where other locations X prime in that same population have an influence on the activation at location X according to a kernel of activation. That kernel is typically localized, so you have a region close to the location you're looking at where neighboring locations excite each other, are positively connected, while at larger distances they are inhibitorily connected, so they suppress each other. And that creates localized peaks of activation as stable states. Those are sort of the units of representation. A peak of activation represents some value along that dimension. And they are stable in the sense that they are stabilized against decay by this local excitatory interaction and stabilized against sort of diffusion across the whole field by the inhibitory interaction. And rather than analyze this mathematically, I want to take you to our webpage where you can use simulators that make that intuitive. So dynamicfieldtheory.org is a webpage we built around a book that we published. And this is the webpage you will be seeing. There's actually a simulator right here that you can play with, but I'm going to use a more sophisticated simulator that we have here to illustrate the ideas. This is a one-layer field, one dynamic field. The blue line is that field fluctuating here a little bit, and below the blue line you see a green line. That's the input to the field. The red line is the activation passed through the sigmoid filter. So currently there's nothing above 0. The threshold is 0. So no interaction in that system. I can load in a interaction kernel, which is represented here as a function of distance. So this is local excitation, global inhibition. This is just a static scheme here. And I want to illustrate a few properties of this. I bring in some localized input. I have some Gaussians I can put in here. And you see here, when I'm below threshold, it's just tracking. The blue line tracks the green, so it's just a low-pass filter. If I go somewhere here, positive activation arises, the sigmoid returns a value, and what you see is a self-stabilized peak. So here you see you have more activation than input, and elsewhere you have less activation than input. So this is inhibition, here's excitation. So this self-stabilized peak is actually, it's bistable with the subthreshold solution. So if I lower input a little bit, the peak is still around. So it's self-stabilizing. And that means that we call this the detection decision. When you first go above threshold, that is actually an instability. It's the instability of that sub-threshold peak. For instance, if I reset the system to this low level, you see that this solution is also there. It's this bistable regime. And then, when that solution becomes unstable, you go above threshold. Sort of like a flip-flop, a macroscopic neural flip-flop, if you wish. There's a lower limit of stability. So if I lower this enough, then that peak is going to disappear, and that will be the reverse detection stability, as we call that. This instability, so this means, unlike a feed-forward network, this system reacts even just to input by going through instability. It makes a decision about the input. And that's actually fundamental to everything that we do, because that creates discrete events that then enable the system to make sequences of processing steps. And I'll show you some of the work around that. These fields also do selection decisions. For instance, if I bring in some other input here at other locations, the peaks are not formed here because of the inhibition. This one came first, so it suppresses that one. There is another instability here. If I make this favorable enough, it can win, suppress this choice. And then if I have similar amplitudes, again, that selection decision is stabilized. So always the idea that you stabilize decisions so you can keep them continuously linked to sensory inputs. I think a notion that roboticists find very intuitive. I want to show two more features here. One is that, this is still activation that's always input dominated. If I remove input, it's gone, but you can actually change the dynamics of the system easily to sustain activation. You can do that by strengthening the excitation here. The simpler form is just to push everything closer to threshold, makes it easier to engage interaction, and then you can actually have sustained activation. That means an activation peak stays around without any localized input, just purely based on excitation, on self-excitation. So that's the standard model of working memory. That's how past sensory information can affect current or future action. Last subtle point here I want to make, if I remove this, go back to the regular regime, that these instabilities in these fields amplify small differences. So I put in here some very small inputs, which you can barely see. There's some locations where there's a little bit of input. And I can give the system just a go signal, just some boost. And then it will form a peak. When it goes through the detection instability, it forms a peak. The peak is sort of the same shape. It's not really qualitatively different from what I just showed you. Out of nowhere, if you wish. And the location of that peak will be biased strongly toward one of those three locations where I had a little bit of input. If I repeat that with some luck, I should sample these different locations over time. So that, first of all, it shows you categories are cheap. You easily get categories out of any kind of inhomogeneity in the field. And it really reduces the demand on learning. You just need a little bit of structure that you can then amplify through the instabilities into macro states. So this recursive, dominant recursiveness of these networks change the role of input. Input is just nudging you a little bit toward certain states, but the important thing is really to go through these instabilities to create instances of the categories you're looking at. Return to my presentation. Also want to mention that this is all embedded in normal neural network theory, so you can also learn connections between different fields in the usual Hebbian way. Particularly important sometimes is when you connect fields of different dimensionality. For instance, a single node, which would be like a zero-dimensional field, you can connect to high-dimensional fields, and that would be the kind of neurons that stand for something, for instance, stand for a certain region. So what I want to do now in the rest was just a quick tutorial on these ideas. Just want to illustrate how one could reach higher cognition in that style. These fields are well understood to play a role in sensory motor. I didn't elaborate there very much, but it's very plausible. But they can also reach what we call higher cognition. That will be the highest at the end, will be something no longer really so directly linked to sensory surfaces. So I want to do this through three examples: how these systems do visual search, how they generate sequences, and how do they model something like relational thinking, and sort of point at how this may be leveraged in robotics. So visual search and scene representation are the very elementary function that every autonomous agent needs. It's the prerequisite to act on an object, is to bring it into the attention foreground. And humans very often also shift gaze and look at the object. I have a chat question here. No. But you can also do this covertly, just shifting your attention in some way. And when you do this with objects, then as a human, you also build a scene representation. That is, you remember these objects. Most surprisingly, perhaps when you don't do that, when you don't attend to an object, then you don't commit it to memory. And if you are interested in that, just Google change blindness, and you will find striking demonstrations that you are blind to major objects in the visual array if you don't pay attention to them. The core idea of how to control attention in neural dynamics can be illustrated here very simply. It's the idea of bringing a peak into the foreground by a cue that you have about the object's properties. For instance, you may have color represented in your system, and so your attention system has the dimensions of your image, let's say two-dimensional image, and the third dimension is a feature cue like that. And so that's a three-dimensional fields in which blobs are instances of items. For instance, if this is the scene you put in there, there would be a blue blob here at this location, and a green blob here at that location, and a red blob I get at that location. So if you bring a color cue into the system, then you can think of that cue as creating a slice of boost. So it boosts all those locations that stand for green, and you can arrange things such that only where a blob intersects with that slice, so gets that extra boost, is the detection instability encountered, and does the system form a peak in 3D blob. So for instance, here in this case, this formed the blob, and you can read out the location of that blob, and that is how you would spatially attend to the object. This can be scaled to real models of visual attention and visual search. This is a complex model we just published that accounts for a lot of data in this domain. It's a model aimed at human psychophysics, although it takes an actual camera image, extracts features from these are so-called guidance features that are very efficient in driving human attention, color, orientation, some kind of size, two-dimensional size feature. Each of those represented in three-dimensional fields of the type I talked about. There is some special mechanism on how to bind across space these different feature dimensions, and there are salience maps, and there's a lot of other stuff. The system actually does have a scene memory, builds a scene memory. It uses the slice technique that I just pointed at to do the attention selection. So I'll not explain that in any detail. Just show you here a little movie. There's sound on that movie, unfortunately, that gets this camera input, has these three-dimensional, builds a scene representations here. These three-dimensional fields are shown here as slices through the three dimensions. And it selects, as it explores the scene, it selects different objects. At the moment, somebody put in a new object here, and there it is. And the system has a change detector, so it notices this change, attends to that object, and it will actually register the feature values of that, and is now designed to look for a matching object that will ultimately be this object. And it does that. Actually, it first, I think, activates maybe this object here at the bottom because it's so salient here, but finds a mismatch of its features in terms of size, and then it loses that, inhibits that, and will ultimately find the right object right here. So this is successful visual search for the object that was cued by that transient. So this is still, of course, an academic example, because this is just to model psychophysical data, but this is actually the machinery of how we feed all the robotic examples I'll do with the scene information. These transitions, the peaks coming up and down, they are emerge autonomously. The scene is stationary except for this one transient, And other than that, the system itself generates a sequence. And how it does that is the next thing I want to show. I got the slide mixed up here. This is the slide I wanted to show first. Sequence generation, of course, fundamental to cognition. You know, any of our actions or thoughts are just steps in sequences of different mental actions that lead us somewhere. And it's a particular challenge to understand how they work in neurodynamic thinking, because neurodynamic thinking representations, we call those here intentional states, are stable states. So they resist change. So how do you get them to change in some orderly fashion? There's some kind of universal architecture that we're proposing that reflects a property of layers in the nervous system, where every intentional state is associated with what we call a condition of satisfaction. That's actually an inhibitory state that has inhibitory connections. And it's driven by two inputs. It gets inputs from the intentional state. That is, any peak that you have somewhere in this picture predicts what sensory information would indicate that what this peak stands for is realized. That would pre-shape the condition of satisfaction field. And then you can get sensory information from the world through some sensor or from some internal state. And if that sensory information matches that prediction, you will get a detection instability here, create a peak. That peak will inhibit the original intention. You get a reverse detection instability. This peak will go away. And as its prediction input goes away, this goes through reverse detection instability, and you delete that too. And so this is how a system, an intention turns itself off. And then generically in an architecture, some other activity, some other peak is maybe has been competing for activation all the time, and then is released from inhibition and start going. So it depends on the architecture what the next thing will be. So in the simulations I just showed you, this kind of transition happened all the time when an object was put into memory, a condition of satisfaction fired and deleted the original attentional peak, and then the next object could come up and so on. So in general, we proposed a couple of architectures. This is a serial order architecture where these nodes all compete and only one of them can be activated. And when the whole system is inhibited by condition of satisfaction, then the connectivity here makes that it's always the successor node that is activated, because the memory node here biases the selection to do that. And that's how you can represent arbitrary sequences. So for, an example is an architecture that has a visual scene representation of the kind I just showed you. It has a neural architecture for generating arm movements, and it has the sequence generation mechanism. This is a system that can observe a sequence of events here and memorizes the serial order of that, the colors, and then on any arbitrary scene, it can act that out by doing the right order of these different color searches here and pointing at these objects. So that it's not a simple copy of the time sequence. It's really the you can have arbitrary time structure on top of this, and it will then act out the serial order of that. This is a more realistic robotic demonstration. This is actually doing something slightly different. It's online updating, how you update the motor plan while the action is going. It's a more complicated architecture that I'm explaining here. The point I want to make is that this demonstration is driven by a neural architecture. It's just one big differential equation ultimately built from many of these fields. And there's no algorithm here other than the numerical solution of the equations. There's no discrete, all the discrete stuff here, the different moments and movements, initiation, termination, all of that just emerges from these instabilities. So that's sort of the radical neurodynamic picture. Now, really high cognition, and it's my last topic here, concepts of relational thinking. So that will be going toward really higher cognition. So for instance, when you talk about a scene, you say the red is to the left of the green. Understanding that means that you are able to bring into your attention foreground this object here that will be on the left. And this is the reference object that this phrase refers to. You would maybe also bring that into the foreground in some other representation. This is an architecture that does that. There are you can sort of guess there would be some kind of kernels here to do that. And I briefly want to talk about that. So here's an architecture that does that. It does that, you know, for cognitive scientists, not for robust. It looks a little bit complex, but actually the components are largely familiar to you now. So up here are concept nodes for colors. So they project onto a color system localized. So let's say the concept node for yellow just gets you a yellow region. There is something about reference and target, so grammatical roles that are represented separately or bound, as we say, that plays a role. This is just another copy of the visual search engine, so three-dimensional feature space fields. There is a movement feature here. This is can also ground phrases. Phrases about, you know, like the red is moving to the blue and things like that. And there are two copies of that, one for selection and the other is for having multiple peaks. These spatial concepts are simple, you know, synaptic patterns that make a lot of sense, like below, you know, would be getting input from this, and left and right and so on, and toward and away would be analogous. You need some coordinate transforms to ground those. So these operators couple into what we call a relational field that is connected to a field where the reference object is represented, a field where the target object is represented. And the relational field is connected by a coordinate transform that centers the target field on the reference on the peak that's in the reference field. And you can have a similar coordinate transform for rotation and other things. So these coordinate transforms are actually also neural operations that I'm glossing over how exactly they work, using the same kind of techniques. So here's an example of this working. So it gets that visual input. It gets the coded into its discrete nodes, the phrase red to the left of green. So this would be the answer, right? This is the left to the right of green. And this is an example where there's another green object and there's nothing to the left of it. This green object is actually a bit larger, a bit closer to the camera, so it will be more salient, will be initially selected. So I'm showing this example because it's a form of hypothesis testing, you could say, that system has to will select this first. It's actually already starting to select this in the reference field, and then has to reject that hypothesis because it doesn't find a matching object, and then it will next select this one. So let's have a look at that. So this is the field where the reference object is represented. It has selected this object. It is now looking for a target there. These are the targets that match red, but none of them actually matches the relation. They are matching the opposite of that, and as a result, the initial selection is inhibited, and there's an inhibition of return that makes that next time it's not selected, and then the correct reference is selected, and then again looking for targets, and then it ultimately finds the right target here. The target on the left was identified. So this sequence of event again just emerges from these instabilities taking place in this neural architectures. There's no algorithm or anything like that. And when I say that it's a hypothesis testing, that's like an information theoretical or information processing kind of description of what that space-time continuous system does. So the last and most radical version of that is to eliminate the sensory surface. You know, here is still an image driving the scene representation, but I can get rid of them. Then I have a purely mental process, and this is using a paradigm that some psychologists are studying, where you get a couple of phrases. In the real example, it's easier phrases like the Porsche is to the left of the Audi, stuff like that. And here in our simplified version, it's color. So like a certain phrases, see an object above the green, a red object to the left of the green, and so on. So you just get these phrases. You have to pay attention, and when you do that, you can answer questions like, where's the blue object relative to the red object? And so we want to build a system that can do that. And you give the phrases through activation of these nodes. It's just a very similar architecture. It just doesn't have this input here. It's a simplified version of the architecture I just showed you. And instead of having sensory input here, it builds its own internal map, and that map is built by applying these relations, to these nodes, and then you bring up peaks here in this relational field that are consistent with the relation and the reference object. The first reference object put in the center of the reference field, and from then on you bootstrap and build a scene map. I'll show you here right here. I'll show you an example here. This is a situation where it has already built a scene map. I put the labeling of the colors here. This is just a spatial representation, but we know how it's associated with color by looking up in the 3D field what color is linked to that. So it has already from previous phrases put peaks here that stand for cyan, red, and green, and now it gets the phrase blue to the right of red. It's encoded in the activation of these different discrete nodes, and it has to put that peak here somewhere, and it will put it here on the outside, and that's so rather than insert it here, the right of red, you could put it either right between these two or outside, and that is actually what humans do. When you ask them to do this, they will expand the map without disturbing previous relationships and put it in here. And here that just emerges from the shape of these kernels. And you can imagine there's a little bit of an inhibition from this object that pushes the peak that's being formed further out. And so here after, again, all this processing is totally autonomous. It's just one peak pushing the next and so on. And so I guess I'm not going to explain the exact sequence. It does that right. And when you have that, you can do inference. Now you have all these objects in here and you can ask it, where is blue relative to the green? And that's the same thing that we did for scene grounding, but we now do it on this mental map. And the system will be able to bring the correct reference and target from the map into the fields, and then ultimately we'll be able to activate the correct spatial relation, which I believe is the blue is to the right. So it should be here the right node that ultimately gets activated. And as that is the case here, does that. So of course you can't really follow the details. So let me conclude. So we have this dynamical field theory is essentially a special case of neural networks in which we're using localist neural representations. So these peaks signify something through their location. Only the neurons in the peak really contribute. And that's a very special subclass where we can use this regular form of interaction, these interaction kernels, to create attractors and their instabilities. So it's much more specialized than, let's say, deep networks. And these detection, selection, memory, and the sequence generation elements can lead to what I showed you, these even somewhat higher cognitive functions. So that's our idea of how we move there. And what the price we pay for that is that these are relatively low dimensional representations representing simple feature values or motor parameters and things like that. You may know that the deep networks and more generally networks might use represent high dimensional information in a distributed way, but it's actually very difficult to design interactions that will create stable states and create decisions and selections and so on. And so we're postulating that the interface between those forms of neural representation that are closer to the sensory surfaces and the motor surfaces, and what the kind of networks we're modeling are essentially the output layers of those systems, where winner takes all, which is really the selection mechanism that I showed you, that would be the interface to the localist representation. So in that sense, what I showed you would be sort of the neural version of symbol processing. So if you said hybrid systems in the beginning, so this would be the neural version of hybrid would be to take deep networks or other kinds of networks, and then that will be the reactive layer that's directly connected to the sensory inputs in the motor systems, and then do the logic, the planning, the sequence generation at this level of low dimensional systems with the strong recurrence that make the peaks and make the transitions. We demonstrate these things sometimes on robots, as I showed you, but it's maybe more like an academic exercise. The real way this might, even if you have a vision for the future, might ultimately impact on robotics would be if you leverage that technology. That is, you directly, for instance, really compute directly on neuromorphic chips the kind of dynamics without going through a numerical simulation of a system like that. So one of my former students is now guiding activity like that at Intel, Julia Sanemirskaya, who actually invented the sequence generation mechanism. And so she does things like drive a humanoid robot with a chip, so not a digital chip. It's digital, but it's neuromorphic. And in this chip, you can sort of program the neurodynamics by just setting the synapses. So these would be, for instance, fields, and they coupled in particular ways. And in this case, for instance, she does something like visual slam on that robot. And there's no numerical simulation of anything. It's really the neurodynamics is directly done on the chip. So that would be one like very futuristic vision of how that kind of program could be made practical in some sense. So thank you.
Thank you, Gregor, for your nice presentation. If someone has a question, please type it in chat, and we'll pose it to Gregor. So while we're waiting for the question, I will ask one from my side. So frequently I'm asked for the question, when the robot will be so skilled as a human being. From your point of view, how far we can have the skills in the robot the same as in a human being, and what are the main challenges right now to make it as skilled in terms of the performance, making some tasks, and probably some cognition?
Yeah, it's a good question, and of course it's difficult and subtle. So, as you know, in artificial intelligence, very typically, you can take a narrow functionality, and then in this narrow functionality, quickly reach human level, even exceed human level. So a lot of the current AI applications to, for instance, pattern recognition and things like that are superhuman. And you can already build simple examples of superhuman performance by narrowing the skill down very strongly, with just maybe throwing something. You know, there's already demonstrations of catching robots that are much better than humans, catching an object that tumbles in a complicated way and that we would not easily catch. These solutions are always, you know, in the end, you can do that without any intelligence in the sense of cognition. You can just narrow it down to be a reproducible, narrow sensory motor behavior. So the real challenge is, how do we get the kind of flexibility, adaptability, the capacity to learn from a single trial, and so on. So it's much harder to formalize that and to say what that clearly means. And so we're actually really interested in this sort of thing, to say, what are qualities that are missing in current robotic attempts? Not necessarily quantities, because you know, if you narrow down, then you can push systems to be very performant. And one domain of where qualities are missing is the one that I discussed with you, which is manipulation of objects, where it's still very hard, even for very advanced robots, to do this well without a lot of knowledge about the objects. And that has to do with perception and with the nature of manipulation. And I think it's a very hard problem that is still quite open. The other domain, the domain that we're interested in, that's maybe a little bit counterintuitive, is something like will, desire, goals, motivation, and so on. You know, there's always this talk about science fiction-like talk that robots will take over the world, but they don't have any goals other than the ones set for them. So there's a little bit of a field called behavioral ecology, where it's a question of how animals, you know, choose to pursue one of their different motivations, which are very simple, and to understand how you could have a system that actually autonomously sort of manages its goals and, you know, does the right thing. That is something not very well developed, and so we're very interested in that. So from that perspective, we're extremely far from humans. I mean, even a small little baby manipulates their parents. The babies are extremely good at social communication, and a baby gets its goals fulfilled. If it wants food, it wants protection, wants warmth, it can arrange for that to happen, even though its motor skills are very limited, but it has that level of having desires and having ways to communicate those desires, and using good cues to seduce the parents to invest all the energy to take care of them. So that would be an example of something that I think that's very, very little developed and totally underestimated. What would be motivations, goals, dynamics of desires, and so on.
Thank you, Gregor, again for nice talk. So we don't have other questions from the audience. So it was a great pleasure for us to hear you. So